So now we're going to talk about the properties of equality. Really what this is balance. So you know a double pound balance, like the justice scales, the two pans with the arm that connects them? That arm that connects them, when it's balanced, is saying these things are the same. They weigh the same. Equations do the same thing. They say these two sides are the same. So the same way that I can add things to the scales or take things off of the scales, same thing with equations. I can double both sides or have both sides, multiply and divide, and it preserves the balance. So we can do anything we want to equations except we cannot multiply by 0 because we will just end up with 0 equals 0. While that is true, it doesn't tell us what x is. And do not divide by 0. It does not go well. All right, so that's what each of these properties of equality are. You can add the same thing to both sides, subtract the same thing from both sides, multiply the same thing to both sides, divide the same thing to both sides as long as it's not 0. And thing can be anything algebraic. So a lot of times it'll be numbers, but sometimes it can be variables. It can be crazy whole expressions, all sorts of stuff. As long as you do the same thing to both sides, you can do whatever you want, even if it doesn't make sense initially. Sometimes we make a detour, but with equations, as long as you're doing the same thing to both sides, and you come back to the path, you should be able to get there. All right. Solve the following equations using the appropriate property of equality. Meh. So to solve the equation, we want to get x by itself. So in all of these, x or n, in the case of number 7, we want to get the variable by itself, has something else with it. And what we want to do is undo it. So there's a couple of ways to write this to make it look all pretty and fancy. But x plus 7 equals 42. So I don't want x plus 7, I just want x. So some people will look at this and think, okay, what number plus 7 is 42? And they might kind of reason their way to the answer, and that works. But what if the numbers were uglier? Then it doesn't reason as much. And the reasoning you go through is, well, if I wanted to cancel out plus 7, what undoes adding 7? Subtracting 7. So we are going to subtract 7 from both sides. Now, in the very technical math sense, there's our equation. And then there's the change we made to the equation. We put minus 7 on both sides. It's on both sides, the balance is preserved. Now, if there's any like terms I can simplify, I can do that. So over here with our x plus 7 minus 7 now, well, plus 7 minus 7 is 0, and x plus 0. Do I really need to even write plus 0? Does it do anything? Is it going to change x? No. And then 42 minus 7 we can calculate, and that is 35. So that is the solution to this equation, x equals 35. Now, you don't have to write that first line of work quite the way I did. In fact, once you get more comfortable with this, usually all you put is like underneath what you're going to change about the equation. But until you're used to it, thinking about it this way, where I have my equation and now I apply a change on both sides, this can be really useful to make sure that you don't apply it in too many places or not enough places. I know it sounds silly, but with really crazy equations, it can happen. All right, so 7 times x equals 42. Now I'll show you what I mean about just throwing it in there instead of rewriting the whole equation. So 7 times x, I want to cancel multiplying by 7. So the opposite of multiplying by a number is dividing by a number. So we are going to divide by 7. So that's what I want to do to get x by itself. I want to get rid of the 7. And to undo it, I must use division. Whatever I do on one side, I must preserve my balance. So if I want to take my 7x's and split it so there's only one, I have to take 42 and split it into 7 different groups and then keep one of the groups. So 7 divided by 7 is 1. So we do have a intermediary thought of 1 times x, but 1 times x better be x. And a lot of times people won't even write the 1 times x or the x plus 0. They'll just write x because that was the whole point of what we were doing. And then on the other side, 42 divided by 7 is in fact 6. So that is our solution to this little equation, x equals 6. So that is what it can look like when you take the starting equation and then make a change. One thing I recommend, this is one of the times when using colors yourself is really beneficial, especially when we start getting to the more complicated equations. Because sometimes you'll go back and look at your work and then you won't remember what you were doing. Like you'll look at it and like, was that in there originally? Did I add an extra step? Like what? But if you have it in colors, you'll get used to, okay, I always write the original problem. I usually write it in black. And then first step in pink, next step in orange, yellowish. But if I can't read that color, then I skip to green, blue, purple, whatever you want. Turning in multicolored work can be problematic, but I've graded it before. All right, so now x over 7 equals 4. So this x is being divided by 7. It's a tiny fraction of x. I don't want a fraction of x, I want a whole x. So this x split 7 ways. Well, I need to undo that split, that division into 7 parts. And I'm going to do that by taking that quantity and multiplying it by 7. So I have 7 copies of this thing. All right, so we're multiplying by this one. I'll rewrite because the 5 is in the way. One side, other side, put some parentheses. I know it can get tedious, but remember, safe math. Because when we start having more than one term and we choose to multiply by a number, that number is going to have to be distributed through. So if you get used to just doing the parentheses now, it'll save you some heartache later, maybe. All right, so 7 over 7 is 1. 1x is just x. And then 7 times 4 is 28. So there is our solution. Now, if you're already looking at these and you're like, I got it. I know what I'm doing. Yeah. I know how to do these. That's fine. These are deliberately one-step whole number equations so far. I'm sure you see the fractions down there. All right, so x minus 7. Goodness, there's a lot of 7s. Equals 28. All right, so I need to cancel out minusing 7. I need to do the opposite of that. So subtracting 7 is undone, canceled by adding 7. So we add 7 to both sides. Now, when we say both sides, it's both sides of the equal sign. So not add 7 to the x and add 7 to the minus 7. That'd be 2 7s on the same side and nothing on the other. So I'll sometimes put this little dotted line to signify do one on one side, do the other on the other. So I see my 2 sides separated because sometimes one side's really long and then the other side's just a number. All right, so here, minus 7 plus 7 is 0. X plus 0 is x. And then 28 plus 7 more is 35. So there's our solution there. All right. Now, our properties of equality hold regardless of what we want to add or subtract to both sides. So with fractions, yeah, we can still do it. Little ugly, but we can do it. So here I have n minus 7/8 is equal to 3/4 apparently. Sure. So to undo subtracting 7/8, I'm going to add 7/8. And then because it's a fraction, I'm going to write it next to it. In order to add these two fractions, we need a common denominator. Now, the good news is I can turn 4 into 8 by doubling it. So I'm going to multiply 3/4, double it, multiply the top and the bottom by 2. And that gives us 6/8 plus 7/8. 6 plus 7 is 13, so we have 13/8. And this is one of those times where I say leave it as an improper, but Ms. Schreier might want it as a mixed numeral. On a multiple choice test, though, there will only be one of the answers. We will not ask you to choose between. But here, this would be 1 whole and 5/8. So depending on what n represented in an actual problem, the 1 and 5/8 might make more sense than 13/8. Like maybe n represents how much bread we have to buy. 1 loaf and 5/8 of another loaf, not 13/8 of a loaf. Oh. All right. So we have plus 3/4. Opposite of adding it is subtracting it. This one is not so nice. But 10 is my bigger number. So next multiple up is 20. I can turn 4 into 20. So we're going to turn both of these into 20ths. So that would be times 2 here. So that is 18 20ths. And then 4 times 5. And that is 15 20ths. So 18 things minus 15 things is 3 things. The things don't change. So this is 3 20ths. That is our solution for x. We could convert that into a decimal, but generally if the problem starts with fractions, you leave it in fractions. It's only on the probability ones where some of the fractions are just ugly and we'd rather see the decimal. Like the decimal has more meaning than crazy fraction. Okay. So there are several ways to attack this. You know what? I'm going to pause it, do this as the start of the next video.